The human brain is a marvel of nature, a biological supercomputer processing vast amounts of information every second while consuming less power than a light bulb. Consider this: the human brain has about 86 billion neurons forming trillions of connections, allowing us to think, feel, and create. Our brains can recognize faces, understand language, and solve complex problems using only about 20 watts of power. Now let's look at computers. They can perform billions of calculations per second and store vast amounts of data, but they're power hungry. A supercomputer can use millions of watts of electricity and still can't match the brain's versatility and efficiency. This comparison raises an intriguing question. Can we harness the power of biology for computing? Can we create computers that think like brains? This is where organoid intelligence comes in, aiming to bridge the gap between biology and technology. It's a fascinating new field that could revolutionize the way we think about computing. Organoid intelligence, or OI, is a groundbreaking concept at the intersection of biology and computing. OI aims to harness the power of brain organoids, tiny, lab-grown, brain-like structures derived from human stem cells. These organoids, about the size of a pea, contain millions of neurons forming complex networks that generate electrical signals mimicking the human brain. Scientists are exploring ways to use these organoids for computing, tapping into their biological processing power. This could lead to computers that learn and adapt like biological brains, a radical departure from traditional silicon-based computing. The potential of OI is enormous, promising more efficient, powerful computers that solve problems stumping our best machines today. They could learn and adapt in ways that mimic human intelligence while using far less energy than traditional computers. Our brains are learning machines, constantly adapting and evolving, forming new connections with every experience. This process is incredibly efficient and highly flexible, allowing us to learn from just a few examples and apply knowledge to new situations. Now, compare this to machine learning, which needs massive amounts of data and consumes enormous energy. AI can beat humans at complex games and recognize speech, but often struggles with tasks easy for humans, like understanding context or adapting to new situations. This is where organoid intelligence could be a game changer. Brain organoids learn more like human brains, forming connections naturally and adapting to stimuli. They could potentially learn from fewer examples and do so using far less energy than traditional computers. Imagine AI systems that learn like biological brains, understanding context better and solving problems in more creative ways while using a fraction of the energy. Brain organoids are revolutionizing neuroscience as 3D cultures that mimic the brain's structure, a big leap from traditional 2D cell cultures. These tiny brain-like structures are grown in labs from stem cells, which are coaxed into becoming brain cells. Over time, they organize themselves, forming structures similar to those in the brain, developing different types of neurons that form connections and generate electrical activity. The 3D nature of organoids allows for more complex interactions between cells, mimicking the brain's environment more closely. Researchers can study how neurons migrate, observe how connections form, and see how brain regions develop. Brain organoids are opening new doors in research, helping us understand brain development and shedding light on neurological disorders. They're paving the way for organoid intelligence, with their 3D structure and complexity making them ideal for this purpose. Our brains are incredibly efficient computers, processing vast amounts of information and doing complex calculations while using surprisingly little energy. A human brain uses about 20 watts of power, less than a typical light bulb, compared to a supercomputer which can use millions of watts. This efficiency gap is staggering, and it's where organoid intelligence shines. Brain organoids could potentially compute using similar principles to our brains, processing information using biological mechanisms that are inherently more energy efficient than silicon-based computing. It's not just about energy efficiency, it's also about processing power. Our brains handle complex tasks with ease, like recognizing faces or understanding language, which are still challenging for traditional computers. Organoid intelligence could bridge this gap, leading to computers that are both more powerful and more efficient. Organoid intelligence isn't just a theoretical concept, it's already showing promise in real-world applications. One area of application is in drug testing, where brain organoids provide a more accurate model than traditional cell cultures. Researchers can see how drugs affect brain tissue and observe side effects, speeding up drug development and making the process safer and more efficient. Another exciting application is in personalized medicine, where organoids grown from a patient's own cells create a brain in a dish genetically identical to the patient. Doctors could test treatments on these organoids to see how a patient might respond to different drugs, leading to more effective, personalized treatments. Organoid intelligence could also revolutionize AI and robotics, with robots potentially processing information more like humans and adapting to new situations more flexibly. Artificial intelligence has come a long way, but it still falls short in many ways, struggling with context, adapting to new situations, and requiring massive amounts of data and energy. Organoid intelligence could change this, leading to AI systems that think more like human brains. These systems could learn from fewer examples, understand context better, and adapt to new situations more easily. Imagine an AI that can truly understand language, grasping meaning and context, or solve problems creatively like humans do. OI could lead to AI systems that are more energy efficient, processing information using biological mechanisms that are inherently more efficient than silicon-based computing. This could make AI more accessible and sustainable, paving the way for AI systems that can run on minimal power. Drug development is a long, costly process, often taking years and billions of dollars to bring a new drug to market. Many promising drugs fail in clinical trials due to side effects that weren't predicted in earlier tests. Organoid intelligence could change this landscape dramatically, providing a more accurate model of the human brain. Brain organoids can show how drugs affect brain tissue in ways that traditional cell cultures can't, leading to better predictions of drug efficacy and side effects. OI could enable smart drug testing platforms, analyzing drug effects in real time and detecting subtle changes that might be missed by human observers. This could revolutionize the drug development process, making it faster, cheaper, and more accurate, leading to safer, more effective medications. Brain-computer interfaces, or BCIs, are becoming reality, allowing direct communication between the brain and external devices. They've already helped paralyzed people control prosthetic limbs and allowed people to type with their thoughts. But current BCIs have limitations, often requiring invasive surgery and struggling to interpret brain signals accurately. Organoid intelligence could take BCIs to the next level, with brain organoids acting as biological interpreters, translating between brain signals and computer language. This could lead to more accurate, more intuitive BCIs that might not require invasive surgery. Imagine a BCI that can understand your thoughts as naturally as another person would, controlling devices with the same ease as moving your own limbs. This isn't just about helping people with disabilities, it could change how we all interact with technology. OI-powered BCIs could enhance human cognition, giving us access to vast amounts of information instantly and boosting our memory and problem-solving skills. Organoid intelligence raises important ethical questions that we need to consider carefully as we move forward. The potential benefits are enormous, but so are the potential risks. One key concern is the nature of consciousness in brain organoids. As these structures become more complex, could they develop some form of awareness? If so, what rights should they have? Privacy is another major concern, with OI systems potentially processing and storing vast amounts of personal data and interacting directly with our thoughts through BCIs. How do we protect this data and ensure that OI systems aren't used to invade our mental privacy? There are also broader societal implications to consider, with OI potentially leading to significant advances in AI and computing that could impact jobs and the economy. We need to think carefully about how to ensure that the benefits of OI are distributed fairly, creating a future where this technology enhances human potential for everyone. Organoid intelligence represents a paradigm shift in computing, not just an incremental improvement in computing power. It's a fundamentally new approach that could reshape our relationship with technology. Imagine computers that think more like us, AI that truly understands context and nuance, and drug development processes that are faster, cheaper, and more accurate. Brain-computer interfaces that feel as natural as our own thoughts are just some of the potential applications of OI. But the journey to this future won't be straightforward, with significant technical challenges to overcome. We need to learn how to grow more complex organoids, develop better ways to interface with them, and create the software and hardware to support OI systems. As we move forward, we must also navigate the ethical and societal implications, ensuring that this technology is developed responsibly and benefits humanity as a whole. The era of organoid intelligence is dawning, promising to be one of the most exciting frontiers in the history of science and technology.